Hey everyone, my name is Justin Houston, and today I'm going to be solving part 2 of exam 1 for our Transport 2 class. And in my first video, I did a scaling of the defined Stefan Maxwell diffusivity equations that I gave us, and using that scaling estimates that I've calculated. We are now going to be solving for the unknown molar fluxes of N1 and N2. So in doing this, we're going to be using Python and Google Collaboratory. Excuse me for that. So to start off, we are going to be actually, so let's just get right into it. I'm going to start with import numpy as np. And what this does is that because we are using Python, we have numpy, which is a library which builds a support for the arrays that I will be coding here in a few minutes. And after that, we're going to go from scipy.integrate, spelled that right, okay, import solve underscore IVP. So what this line that is type means is that this function integrates a system of ODEs, given an initial value and an initial value problem. So our next line, from scipy.optimize imports roots. And what this is going to do for us is within the scipy library, which is also with Python, as you can tell with the py at the end. There's a module called optimize, which I called for here, and this offers a function or a method called root to find a set of roots within a set of simultaneous equations with those ordinary differential equations that we scaled in our first my first video here. So our next line, we're going to go with from plotly subplots, and we want to import that as well. We call it make subplots. So what this is going to do is this creates a set of graphs, which are the subplots in this case, based off tabulated data. And if we had multiple graphs, they'd be placed side by side, but in our instance here, we're only having one subplot. So from there, we want to import plotly graph objects as GO, I misspelled objects. So what this is going to do for us is this is once again importing that scatter plot, in which case that scatter plot is considered a graph object, and in this case that's identified by the GO, and that's coming from the objects library within Python. So now we want to import once again plotly as PO. And what this does is, and along with the next line that I'll be typing as well, this is going to, actually let me just type the next line real quick. PO.templates.default. And this is going to equal, we'll call it plotly dark. And I will explain what that means here. So with that line that is typed in the previous line, this sets a graphical template to a dark background. So what's the word? It starts off having the setting of a light background, and I just changed that with the 2 lines of coding that I just imported there. So now we can go on to, actually forgot to hit Shift Enter so that runs. Okay, So now I have already inputted our givens, and I will run through that now. So with D12, we already know that that is the Stefan Maxwell diffusivity constant for components 1 and 2. And that's going to be, for all constants for diffusivity, it's going to be meters squared per second. And I have those three there, 1, 2, 1, 3, and 2, 3. We next have the given pressure, which is in pascals. Next is temperature, which is given in kelvins. Next we have our ideal gas law rate constant, which is in joules per mole per Kelvin. Then we go on to delta, which is given, and I actually forgot to insert its units, which is in meters. And then from there, we have N1, which N1I, which is the molar flux component 1, which we just saw from my previous video from the scaling. So that's why it is at 1 times 10 to the negative third. And this is going to apply for molar flux of component 2 as well. And that I is for the initial guess. That is why I included that there with its components. And then we also have the given what is it, mole fractions. So for component 1, which was acetone, I believe that was 0.319, and then the mole fraction for component 2, which is methanol, was 0.528. And we also here want to add a few other things, equations that were used in those ODEs, the ordinary differential equations, with that Stefan Maxwell's. So we also know concentration is equal to P divided by R times T. And we also know that we also wanted to add in a few other variables. So we're going to add in F13, which is just a random letter that I made up to substitute for simply the denominator where we found the order of magnitudes in the previous video. So for F1, actually, let me start from the basis. F12, that's going to be equal to the concentration times delta divided by, actually I messed that up. We want that times the Stefan Maxwell constant divided by delta. That's where that comes into play. And then we want to do the same thing for F13 and F23. So actually forgot to hit enter. Sometimes that just doesn't work. F13 is equal to concentration times D13 divided by delta. Oh, I already messed that up. D13 divided by delta. And then last F23 is equal to molar concentration times constant of diffusivity 23 divided by delta. And once again, my enter button did not work. So, all right. So anyways, we want shift enter on that. So next we're going to be continuing this on by starting to solve for those molar fluxes based off of those initial guesses. So in doing so, we want to start this code off. Okay, so defining that N1I, which is a molar flux of component I, we're going to set just component 1 equal to what I just stated, N1I. Actually, you know what? No, we do not want to do that yet. Excuse me for that. First, we want to define a function. So we're going to define df, dy, which is going to have our independent variable eta, which is what we defined in I defined it in my first video as that variable substituting to help with the scaling, and then our dependent which is the mole fractions. Get that in there. Next we have our mole fractions, which is y1 equal to y at 0, where 0 is component 1 with acetone. And then we're going to do the same for y2. It is equal to y of 1. And then y3, we know based off of just general definition that y3 can be solved due to the fact that the total mole fraction is going to be equal to 1, so we can subtract y1 and y2 from 1. So we're going to do that here. 1 minus y2 minus y1. Enter. Next, we're going to do return NP array, parenthesis, brackets, and then this is where that Stefan Maxwell ODE comes into play. So we have y1 times, here's my times button, times n2, which is the molar flux of component 2, minus mole fraction of component 2 times n1, which is molar flux of 1, parenthesis, and then we divide that obviously from the variable that I just inserted this time around, which is that f12 variable, which is just in replacement of the denominator. Then we subtract that, obviously, mole fraction of component 3 times n1 divided by, once again, that new f variable f13, comma, and then just to keep our lines even and kind of in order, we want to just shift that down so it doesn't extend too long. So then we get, can't forget the parenthesis, y2 times n1 minus the mole fraction of 1 times molar flux of component 2 divided by f12 minus y3, which is the mole fraction of component 3 times molar flux of component 2 divided by f23, and bracket, and then parenthesis. Actually, it already gave it to us. Yeah, it already gave it to us. So then we want to insert a solver for this. So we're going to say solve. And let me explain what I forgot to explain that return. So this is going to return what I just typed there. It's going to return the value of the right-hand side of the ODE, and that's pretty much it. You can see it's got the numpy in there, and the return value of that ODE equation, as I said, pretty much from the beginning. But just to reestablish that, then like I said, I bring in the solve underscore IDP. dy, which is our callable, comma, our independent variable, which has a range of 0 to 1, comma, then we want our dependent variable, which is like our initial states pretty much. So we say y1i, comma, y2i, those mole fractions, and bracket or in parentheses. Then we need our method. Method, and we use what's it called, radow, if I'm even saying that right. And then our dense output, which is equal to true. And So yeah, I think that's all we need for this. Trying to think what else. Um, yeah, we have the integrated method, which is that RADOW. Um, so yeah, I think that's good. So let's just try to compute this real quick. Give a little space in between that. Invalid syntax. Hmm. Yep, I forgot a parenthesis. Should be good there. Uh, Clear that. Let's try that again. Okay. Actually, no, we wanted that to output something, so um, my controller is, my mouse, excuse me, is lagging behind a little bit. Hmm. Oh, I simply forgot to define this. Um, oh, what I meant to say is define N1 and N2, which I was doing at first, but then I just stopped for some reason. I just forgot to. Um, N2I. Those are those initial states again. All right, let's try to run this again. Okay, so this gives us an output. We know we're like on the right track here, but this is not exactly what we want because you can see we have with the y variable, it's going negative there, which we know we don't want. We want it as close to zero as possible. Well, we want it at zero. Um, so we know we are not quite there yet, but we know we can assign a new, or we can assign a variable to this solve IVP. So we'll just call it res for result. Um, and now that we have that in there, just shift enter again one more time. So now that is stored under the res variable, and we can access that field. So what we do want to, excuse me, what we want to do next here is do a res.sol at 1. And this allows us to access that solution that we just found for any value of eta. But what we now have to do is correctly solve for, so you can see we have that array, the negative value. We don't want that. So what we want to do is now correctly have a correct guess for N1 and N2, the molar fluxes of component 1 and 2. So what we are now going to do is define a completely new function here. Above, when I defined the molar flux of component 1 and 2. So here we're going to define f of, let's just call it n, and we can now change these n1 and n2 values we can just call N1 equal to N0, which is acetone, like I said before, and then we want N2 being equal to the N of 1 of methanol. So then we have that define, we have all that stuff that I already typed out. And getting this, we can now try this again. Invalid syntax. Let me think about this for a second here. I don't know. Is it? Yeah, I think it's because it's capitalized or something. Let me just try getting rid of that. Yep, I clicked at the wrong spot. That should be better. Really? I'm not sure why. Maybe they just need to be indented. Let's just hope for that. That's not what I wanted. I think I also forgot to return with that res.sol. Yeah, it's just the indentation I forgot here. I think I could, yeah. Let's just try this one more time here. Sorry for the delay. Maybe that's really. So the indent was fine. Let me just get rid of the return here. I still feel like I'm missing something. I don't know, man. Hmm. Well, I'll just keep trying to plug along, see if I can figure this out or not. I feel like I need a return in front of res.solve, but I can't remember to be honest. And it's solving. Still got that negative though. Anyways. So anyways, I'm just gonna keep going. We'll bring in the root now. F comma N1I comma N2I for that initial state. What this is going to do is the root solver will return all values leading to 0, which is why we want to use this. And this should give you the answer. That we are looking for. Sorry, I totally just zoned out there. And then we are also going to bring in, oh wait, no, we're not. Let's just solve this real quick. So I'm going to be picking up again where I just left off. Apologies, I just had to sit down and think a couple things through. So what we're going to do here is, you see I still have that syntax error. And what we need to do is actually correct the indentation. So we're just going to tab once for both of those. And then let's try it again. Okay, so yep, we have it running this time. Looks good. So yeah, there's nothing else I need to add for that. So we're going to move down to the next cell of code. And what I want to start with is, let's start with root, which will be root f bracket and 1I, comma, and 2I, which is the molar fluxes at the initial state. That returns us an array here that we are looking for. And as you can see, it actually gives us the values that we're looking at down here at the bottom. And we know that those are actually correct because they're leading to 0, and also because of their order of magnitude is correct as well. It's at 10 to the negative 3. And this should be giving us our molar flux values that we did not know at the start. So since we know that that is correct, we want to give a variable name to this. So we're going to say that's equal to res. If I could type it in the right spot. Excuse me. Res equals root. And then we also do want to add in a res.x because this now gives us the array of molar fluxes, or at least it should. Once again, output that, including the correct order of magnitude. And yes, it just simplifies it. We have it stored as res, which we can now access at any given point. So moving on here, we now want to once again solve this. So in doing so, what we are simply going to do is just kind of cheat our way through. We are going to basically copy and paste everything from the previous row, from the previous code of text. So copy that, add it below what I just typed. So we have that in there. Um, and what we're basically going to do is redefine N1 to include this res.x. So with that, I'm just going to get rid of that res.x real quick, just to simply type it in with the n below n1 value of the molar flux of component 1. So now res.x 0, and then we want to do the same thing for n2. At res.x x, and then we have that defined. Okay, I think everything else looks good. We just want to make sure this res at the bottom here lines up. It should. Okay, I think everything looks good. Let's give it a shot. Okay, it's saying unexpected error or indent with the N1 definition that I gave. So let me fix that N1. Maybe the same thing for N2. Let's try running it again. Once again, unexpected indentation for the defines. I think I just need to fix all this real quick, so give me 1 second here. Okay, try that again. Yeah, it ran correctly. Good, good, good. So now what we want to do is plot this data here. So in first doing so, we want to generate a set of linearly spaced values with an array basically. So what we're going to do is say underscore plot is equal to numpy dot space. We'll say from 0, 1, 51. And like I said, this is just creating a set of 51 linearly spaced values. Then we also, oh, sorry, I forgot. I'm having some errors with my coding here. Keep rolling here. We want to bring in that res.sol again for the eta underscore plots. Actually, let's just make sure that this is first displaying that. Okay, yeah. So that's sol underscore eta underscore plots. And there you go. There's our giving us that array of 51 different values. We'll close out of that real quick. And then we can, since we know that is working correctly, we can define that res.sol of eta plot, and we'll just put for the solution SOL and give that an equal shift enter. So now that is stored under SOL, we can bring that into our future equations if desired, which I believe we will be doing. So anyways, now to the official plotting method. First, just go off of defining make our subplots with rows equaling 1 while columns equal 1. Yeah, that's it for that part. So what that does is that this graphs our figure in one plot, which is why I only included one row and column We'd obviously have more if there was more subplots. So next, we do big, adding a trace to our subplot with the general objects scatter. X is equal to our eta, which remember eta is that variable that we defined while scaling. Excuse me. X equals eta underscore bot times delta dependent y equals that sol we just defined at 0, which is going to be that first term, which we know we can name that as the acetone. Okay, can't forget that last parenthesis. What I'm going to do now, we have to do the same thing for the other two components. So we can just copy and paste that. But then I got to go back in and redefine these. Second term was methanol. And we know that is the second term, so it's going to be of 1 in brackets for the sol solution. And then yes, air is the last one. And as I defined previously, we know that air can be found from subtracting, taking 1 and subtracting the mole fraction of component 1 and component 2 from that. So what we're going to do here is we're going to do 1 minus sol 0, and then we also have to include that minus sol bracket 1. Okay, I think that looks good. So let's see how this plots out. Yep, I think I got everything correct. And boom, I believe this is what the graph should look like. As you can see, we have the air going upwards while we have methanol and acetone, the blue, going to 0 there, which is what we want to see. So once again, this is my example on how to solve for unknown molar fluxes based off of scaling 2 different ordinary differential equations that were both Stefan Maxwell equations. So yeah, that's it.